Welcome to this video tutorial about feature selection with AI Studio. Feature selection can be used just to understand better the dataset and understand which features seems to be most useful to predict the thing I want to predict about my dataset. And they can also be useful in the case that you have more features, more variables, more attributes, all those words are synonyms, than you would like for the size of the dataset. If that rule of thumb that the number of dimensions of the feature space, the number of features raised to the square is not much smaller than the number of instances, then we have too many features for the number of instances. If most of those features are metric, we'll see a very interesting transformation in another video, principal component analysis, that can be used to address that problem. But if most of those features are non-metric, if they are nominal or ordinal, in that case, feature selection can be used to remove some of the less useful features. We'll start, as always, with the iris dataset, a dataset we are already quite familiar with, where in the visual exploration video, we saw that in the first attribute, all the different instances are quite mixed, all the different instances of the different species. The second attribute, they also quite mixed, maybe not as much, but they also, well, even more, excuse me, they are even more mixed. Over here, at least there is this region over here where it's clearly Setosa, and that region over there where it's clearly Virginica. There is less overlap in A2. There is a little bit overlap pretty much everywhere, but at the very extremes. And A3, there is a nice separation between Setosa and the other two species, and there is not too much overlap. There is a little bit overlap between the other two species over there, and more or less the same goes for A4. Maybe there is a little bit more overlap here. Well, this is not clear because this is just single instances and 3 instances over there. So over here, we already know which attributes are the best ones. If within the operator sections of AI Studio, you go to feature weight is how AI Studio calls the different filter methods for feature selection. Filter methods, they created some ranking where each of the attribute was assigned a score which reflected its quality. When you have so many ways of pretty much measuring the same, because all of these, they have the same goal, there are some nuances, and some of these operators can only be applied to datasets which are completely metric, others to datasets which are completely non-metric. Some of them, a good part of them, can be applied to datasets which are mixed. They can have both types of features, but there are some nuances, and not all operators can be applied to every dataset, depending on the type of features that you are working with. But in any case, when we have so many criteria to measure the same thing, it typically means that all those criteria are not really good, because we have one really good metric, we wouldn't need all of the others. As I already explained in the theoretical part of the course, all these criteria, they are no better than rules of thumb. They are not definitive criteria. So what I typically do is to use several of them and to check if they all agree. If they all agree, I feel more confident that they are probably right. And if not, I have much more doubts whether they are providing useful information. Information gain is a feature selection, well, it's a criteria that can be used for feature selection, which is based on entropy. It'll be covered in detail later in the course, because it's one of the metrics that is used by decision trees to build the decision trees. Gain ratio is a correction applied over information gain. There is a small nuance that can be useful when we have attributes which look like unique IDs. The chi-square statistics computes the chi-square statistics, as the name implies, between each of the attributes and the class. And for example, relief is a sampling method. So I'm dragging 4 different operators, 4 different filter methods to measure exactly the same thing. And again, if all of them agree, and that's likely to happen for the Iris dataset because it's a simple dataset, then I'll trust the results. If each of them give a very different results, then probably the final conclusion is that we don't really know which are the best attributes. Let's start by information gain. The information gain is over here. If I sort the attributes, the most useful seems to be A3 and A4. It's assigning them the same value, followed by A1, and the least useful is A2. Indeed, A2 was the one where there was more overlap among species, and A3 and A4 is where there are more separation. So indeed, we fully agree with these results based on the visual exploration. If we check gain ratio, okay, sorry, I'm doing this in a virtual machine, and sometimes RapidMiner or AI Studio has the math custom of just hanging. So this was information gain. Now it's alive again. This is gain ratio. The values change a little bit from 0.998 to 1, but still is more or less the same order. A3, A4 are the best ones, followed by A1, and the less useful is A2. The chi-square statistic, the order is inverted. A4 appears first, A3 second. In the other cases, it was the other way around, but still they have much higher values than A1, and A2 is the one with the lowest value. And the sampling method got exactly the same result as chi-square. A3 and A4 are by far the most useful, the highest ranked, followed by A2, and the least useful A1. So in this case, there is no surprises, and all of them agree in that A3 and A4 are much useful than the other two, and among the other two, A1 is more useful than A2. These are filter methods. They create a quality metric for the usefulness of each of the features. If under modeling you go to optimization, there is a feature selection section where we have different strategies to search for the combination of the attributes. Again, sorry about this, but it keeps getting stuck. I have to minimize it and maximize it. For example, in the case of forward selection, what it's going to do is to start building a machine learning model with a single feature, compute a performance metric, and then add a second feature. With both features, it improves, it maintains both features. If not, it removes that feature, and so on. I have to feed it the data, and in the case of feature selection, instead outputting a ranking, a quality metric for each of the attributes, it will output binary answers for each of the attributes. Was this attribute used in my model or not? And I actually need to go inside this operator. This operator you see that has double border. Those are nested operators. Those are operators that need operators inside. Because over here we need a machine learning model to test how good each of the attributes are. We have not covered yet what machine learning models are. So you're going to have to bear with me and just trust blindly what I'm going to do. I'm going to look for a machine learning model, a decision tree, for example. I need to feed data to it, but I also need to compute how good the training of that machine learning model was. So before feeding the data to it, I'm going to need to look for the split data operator, which, as the name implies, allows me to split the data in different sets. I'm going to set up the split data operator in such a way, I'm clicking twice in add entry, that the first output port is going to contain 70% of the data and the second 30% of the data. 70% of the iris data is going to be used to train the decision tree. And then we're going to apply the model that we have learned. We're going to apply that decision tree. That's the model, that's the decision tree over the data that has not been used during training to avoid overestimating the performance of the decision tree. And finally, I need to compute some metric to judge how good the decision tree it is. It's going to be just accuracy. We'll see this in more detail in another video, but again, this splits the data. 70% of the data is used for training the decision tree. The trained decision tree gets fed over here, and also the remaining 30% of the data. The decision tree makes prediction for the remaining 30% of the data, and we compute the accuracy metric. I just press, okay, it just got stuck again. In order to exit these nested operators, you can press or you can just go up here. If I run the process, the result I got is that use just A4, which could be a fine result for this dataset. And again, this was performed using a forward selection. If instead using the forward strategy of adding one feature at a time, I right-click over the operator and I go to Replace Operator, Modeling, Optimization, Feature Selection, and I use backwards elimination. I start with all the features and I try to remove one feature at a time. Now I got a completely different answer. A4, excuse me, still chosen, but also A1 and A2. If I use different strategies, I'm going to get different results. In this case, I could actually try all the possible options, but using the optimized selection brute force, which tries every single combination, which is 4 factorial in this case, and this will be feasible. I don't know why it does that, but it just wants me to connect it again, and it's again also choosing A1. If you have more than about 10 features, you won't be able to do the brute force strategy of trying everything. You may, however, use the evolutionary option. In the evolutionary option are the genetic algorithms, where, for example, we can specify that we want a population sample of, let's say, 100 decision trees, and we're going to allow it to evolve through 40 different populations. And again, in this case, it shows A4 and A1, which actually probably is the most optimal solution, honestly, for this problem, because A3 and A4 are the best attributes and they more or less provide the same information. Once I have used one, I don't need the other. The ranking methods, they are always telling me that A3 and A4, they are the best ones. And while that's true, it's also true that the correlation between A3 and A4 is 0.998. It's a very, very, very high correlation. And that means that they are providing almost the same information. And when a model has used one of those features, the other provides very little value. Excuse me. If I connect over there, the operator is just computing the correlation of the attributes that were selected by the grabber method. So let's first compute the correlation matrix over all the attributes and then feed all the attributes to the feature selection. And over here we see, well, it was not 0.98, it was 0.96, but still a very high correlation between those two features. So probably this solution over here of use A4, after that forget about A3 because it's giving you pretty much the same information, and then A1 still provides a little bit of information. This is possible for probably the optimal solution. If instead using such a simple data set, we use a more complex data set, the Titanic, I need to specify in this case which is going to be my class. By default, that dataset doesn't have any class. So I need to specify in the set role operator that the attribute survive is the thing I want to predict. Therefore, I need to assess the value of that attribute, of each attribute, to predict survive. And if I do this, well, you can see that in this case, the evolutionary algorithm is taking a few seconds to run in my computer. If I had select the brute force one, it still would have taken way more time. And in this case, I'm unlikely to see such a cut clear results for multiple reasons. Let's start by information gain. According to information gain, the best attribute to predict whether a passenger survives or not is the name of the passenger. We already saw that unique IDs are useless with analytical purposes. Right now, AI Studio doesn't know that that's a unique ID and is considering that is a very, very, very good attribute to know if you survive or not. And the next one is the ticket number, which instead for babies is synonymous with the name. It's a proxy for the name. And next one, the cabin. Again, in the cabin, there may be 1, 2, 3, 4 people who are related of the same family. And after these things, which more or less are unique identifying people, we have gender. We know that indeed gender was very useful, and other attributes. The correction that gain ratio applies over the dataset precisely takes into account that I want attributes which are useful to predict the class, but I want attributes that they don't take a ridiculously large number of different values, such as the name. In this case, sex is the most useful attribute. We already explored visually the dataset, and we know that's the case. Age is also useful, and the name comes third. If we check relief, in this case, it seems that the most useful negative in relief means is not useful. The better one is passenger fare. And you see that the ranking is very, very, very different from the other rankings. And if we check the Grapper method, which is using genetic algorithms, is telling me to use the name, the ticket number, the cabin, the unique IDs, whether the passenger made it to a lifeboat or not, and the cabin number. In this case, the results are quite not conclusive. There's not a very clear conclusion. However, we are doing a very lazy job by asking all these operators to judge the whole data set without thinking too much about it. The reality is that there are some attributes, I'm going to look for the select attributes operator, that should not be taken into account in the analysis because I already know that they are useful. So I'm going to tell that operator to exclude the attributes that I'm going to select. I'm going to select a subset. The cabin more or less uniquely identifies the passengers. I don't want rules which said if you were traveling in this cabin number, then you survive or you die. The name, the same goes for the name. The ticket number down here is also a unique identifier. And by the way, despite it's quite useful to know whether somebody survived or not, I also want to remove very likely the lifeboat number. Why? Because if a passenger made it to a lifeboat, it was extremely likely it survived. And if a passenger did not make it to a lifeboat, it was almost certain it will die. Sometimes there are attributes which are not unique IDs, but that given the problem that I am analyzing, it doesn't make any sense to take them into account in the analysis. For example, in the last year, many students of mine have used COVID-related datasets for this course, for the final project. If your goal is to predict whether a patient is going to have severe COVID or not, using as information whether the patient was admitted to the hospital or not, and especially whether it was admitted to intensive care unit or not, is cheating. If the patient was admitted to the intensive care unit, it of course developed severe COVID. If not, it wouldn't have been admitted to the severe unit, to the intensive care unit. And if it was admitted to the hospital, it's clear that the patient did not develop a mild case of COVID. So using whether the patient was admitted to the hospital or intensive care unit to diagnose a disease is cheating. Using whether you made it to the live vote, from my point of view, it would be cheating. I want to know if passengers of different ages with different number of families or traveling in different classes or of different sexes, or whether they got in the boat in one port or another. I want to know how these features relate to surviving, and not whether you actually made it to a live boat and therefore almost certain you survive. If I remove those attributes and I just keep the attributes which actually make sense to analyze, I'm probably going to get more clear-cut results. So in this case, in information gain, the most useful attribute is gender, followed by the class, the fare, the port of embarkation, age is down here, at least gender is the best one. In gain ratio, in this case, sex and age, which you know are related, and then number of relatives down here. In relief, sex is the first one, followed by passenger class, port of embarkation, age is down there. In the case of the chi-square, sex is the first one, passenger fare, and passenger class first, and then fare, and so on. By checking these different filter methods, the conclusion I could draw is that sex is the most useful, or seems to be very useful, because it was the highest ranked by all the methods. And then things are a little bit more fuzzy. If I check the Gropper method, sex was chosen, port of embarkation was chosen, and the passenger class was chosen. Those also tended to be ranked higher in the other methods. Age, in this case, was not chosen. Again, if I had to write a report and explaining what I saw using feature selection methods, the more conclusive thing, the most conclusive fact is that sex is the most useful feature, is definitely relevant, and then maybe passenger fare, passenger class, age, they can also be useful, although that's less clear. In general, when you use feature selection, you may, at least for complex data set, get results which are not completely clear. They still can be useful, and there can be some attributes where were consistently selected by most of the techniques. Therefore, those seems to be useful, and there can be others which are less conclusive, and you cannot really extract any conclusions. If you were in the situation where you need to remove some of the features, then go ahead and remove the ones which were ranked the lowest consistently or that were not selected using Gropper methods. And if you were just exploring the data, but you didn't want to, or you didn't have to remove any attributes, then just extract whatever conclusions you can from the results and move ahead in the analysis. See you in the next video.